Hello lovely humans, Jen Foxbot here. In this sub-series that I'm calling Math in Making, we are going to look at the math that pops up when we build projects. Yay! So useful! So if you have topics that you want me to cover, by all means, please let me know. We are going to start with ratios and proportions because these pop up in all different types of projects. They're particularly useful for planning and prototyping. And they're something that anyone can learn, especially if you're into making projects. So what we're going to do in this video, I'll talk about what they are, we'll do an example, and then I'll cover some things to keep in mind when you're doing ratios and proportions. So what is a ratio? Well, let's say I wanted to build a sweater for a meerkat. As one does, a meerkat is a different size than me, so without being able to fit a meerkat as I make the sweater, how do I figure out how big to make it? Well, I can look up the average height of a meerkat, I can measure my own height, and then I can measure my own sweater, and I can use the ratio of my height to the meerkat's height, set up a proportion using the size of my sweater, and calculate the measurements of the meerkat sweater. Very important work. So, a ratio is a relationship between two different things. The ratio is the meerkat height to my height. It might be represented as a fraction, the meerkat's height over my height, or it might be represented with a colon, which really just means a fraction. And then the proportion is setting two ratios equal to each other so that you can solve for the thing that we don't know. In this case, the size of the meerkat sweater. So let's look at an actual example, and I'm going to pull from my real world experience because I love doing that. I had a student that really wanted to build a life-size, and by life-size I mean human-size robotic table that she could drive around with remote control. Hilarious. Yes, absolutely. However, big tables are challenging. It takes a lot of expensive parts. It takes a big motor. There's a lot of pieces involved. And so I was like, we should build a smaller version, a scaled version, so that we can learn about the pieces involved in building a remote control robotic table. Cool. So what we did, because my student was into American Girl dolls, we decided to start with a robotic table sized for an American Girl. Okay, so this is where, to figure out the proportion that we need to set up, we need to gather some information. So what do we know? We know the doll height, which is 18 inches, or 46 centimeters. So we actually measured this. You can also look it up. We know the average height of a table. Average table height. Again, this you can look it up. We measured a table that was in the room that we worked in. An average table height is 30 inches or 76 centimeters. And then we used my student's height for this project, but I'm going to use my height because I'm kind of smack in between the average height for men and average height for women. And we'll talk about, how do we decide these types of things that are a little squishier than these two. All American Girl dolls are the same height. The average table height, well, it's average, so it might change a little bit, but not by much. But humans are wildly different heights. So that is going to change our proportion. We'll talk about that at the end. So I am 5'8". For now, suffice to say, pick something like the average. That can help when you make these kinds of decisions. And so this is 172 centimeters. And then the last thing the thing that we're looking for that we don't know is the height of the doll table. So I'm going to say doll table height equals, I'm going to pull out a different color because I like colors. Question mark, what is this? Ah! This is where ratios and proportions come to the rescue. Okay, so there are always multiple ways to solve the problem. The way that my brain first looked at this was to set the ratio was to use the ratio between the human height and the doll height. I'm going to use a metric system because I think it's easier. The ratio of the doll height to the human height is 46 centimeters divided by 172 centimeters. Basically, we want to figure out what is the fraction of the doll's height to my height. That's kind of a weird way to say this. But this is the ratio. So the doll's height is on top, my height is on bottom, and that tells me how those two heights are related. And then we set that equal to the ratio of the doll table height to the average table height for the human. And so this is where we do need to be careful here. We want to be consistent. If we put the doll height on top of the first ratio, the doll table height needs to go on top of the second ratio. And so the average table height goes on the bottom, 76 centimeters. And then we solve for x. Yay! So to solve for x, we just multiply by 76 on both sides. So 76 centimeters times 46 centimeters divided by 172 centimeters equals 20 centimeters. Yay! Da da da! We're done! There are multiple ways to do ratios. You also could do the table height ratios. Sorry, the human table height to human height ratio and the doll height to the doll table height. So what that would look like is the human table height, 76 centimeters, divided by the human height, 172 centimeters, equals the doll table height, which is our unknown, to the doll height. Again, the important thing is to be consistent. So in this case, in our first case, we have the doll height and the doll table height. In this case, we have the human table height and the doll table height. So the table height needs to go on top. The height of the humanistic figure goes on bottom. Okay, so this alone is a ratio, this alone is a ratio. When we set them equal to each other, we are able to solve for x. And we're kind of using the relationships of each to find the unknown. Okay, cool. So that's it for ratios and proportions. I'm going to end by talking about a few things to keep in mind. So you probably noticed that I used the metric system. The first thing to keep in mind, units. Even NASA engineers mess up with units. So it is a pervasive problem. It doesn't matter how good you are at your job, you always want to check the units. I like the metric system because it's easy to be consistent. I'm not mixing feet and inches. Definitely done that before. It is up to you, but you do need to be consistent. All centimeters, all inches, all feet, totally fine, but none of the mixing going on here. No feet and inches, none of the 5 feet, 8 inches. Convert that into inches or convert it into feet. Pick one. Okay. The second thing, precision and accuracy. So these two kind of feed into each other, but they are slightly different. So accuracy is basically like how much of an accurate representation are you trying to build to your full scale model? I know I'm terrible. I use the word in the definition. I was trying really hard not to. And precision will kind of feed into that. So for example, I rounded to 20 centimeters. That was precise enough for what we were looking for. It wasn't critical that all of the parts of our table were an accurate representation of the full-scale model. That said, if you do need an accurate scaled version, you're going to need to have a higher precision. Okay, and number 3 is size of your scaled model. For us, like I mentioned, the key goals were learnings, and so the size was kind of arbitrary. It was really what teaches you the basics of robotics. But if you are trying to build an accurate representation, you need to think about the size of your scale model because you can't get all of the detail in a super small model, and you're also going to get different forces, different torques, that type of stuff. So definitely think about size. Okay, I'm going to leave it there for now. Let me know if you have any questions about ratios, proportions, or other types of math as we make projects. Yay! Thank you very much for watching, and I'll see you next time. Bye, friends!